Welcome to a lesson on triple integrals using spherical coordinates. In a spherical coordinate system, a point P in space is represented by an ordered triple rho, theta, phi, where rho is the distance between the point and the origin, as we see here in green. Theta is the angle counterclockwise from the pole or positive x-axis in the xy plane, here in blue, and then phi is the angle between the positive z-axis and the point, as we see here in red. We also need to be familiar with the equations used to convert between spherical and rectangular coordinates. So you may want to copy these into your notes. Let's take a look at a triple integral using spherical coordinates. If we have a triple integral in rectangular form as we see here, this is how we write it in spherical coordinates. And there are several things that we should recognize here. First, the function must be expressed in spherical coordinates, where x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. And then notice that differential v is equal to rho squared sine phi d rho d phi d theta. So there's an extra factor of rho squared sine phi when converting to spherical coordinates. And just like any other triple integral, we can change the order of integration. Let's go and take a look at an example. Here we want to integrate our function over the solid region x squared plus y squared plus z squared is equal to 4. We should recognize this as a sphere with radius 2. So this represents our region of integration. Let's go ahead and set this up. First, let's convert our function to a function in spherical coordinates. Well, x squared plus y squared plus z squared is equal to rho squared. And then because we're converting to spherical coordinates, we have extra factors of rho squared sine phi. Let's go ahead and keep the order of d rho, d phi, d theta. Let's start by taking a look at the limits of integration for rho. Remember, rho is the distance from the origin to a point on the surface. And because the radius is equal to 2, the limits of integration for rho will be from 0 to 2. Next, for the limits of integration for phi, remember phi is the angle between the positive z-axis and the points on the surface. So to get the entire sphere, rho would have to be from 0 all the way to pi radians. And then for theta, the angle between the positive x-axis and the points on the surface, we have to rotate all the way around a circle in the xy plane. So theta would be from 0 all the way to 2 pi. Let's go ahead and rewrite our integrand and then we can integrate. So we'd have rho to the 4th sine phi Let's go ahead and evaluate this on the next page. So treating phi as a constant, we'll have 1/5 rho to the 5th sine phi. Replacing rho with 2, we'd have 32/5 sine phi. And then when rho is 0, this would be 0. And now we'll integrate with respect to phi. That's going to give us negative 32/5 cosine phi. When phi is equal to pi, cosine pi is -1, so I'll have positive 32/5 minus, and then when phi is 0, cosine 0 is 1, so we'll have a negative 32/5. So we'll have a positive 64/5. So we'll have 64/5 theta evaluated at 0 and 2 pi. When theta is 2 pi, we'll have 2 pi. When theta is 0, we'll have 0. Like we'll have 128 pi fifths for this triple integral. Let's go and take a look at another one. Here we want to integrate the function over the region inside x squared plus y squared plus z squared equals 1 in the first octant. So this would be our region of integration. Now let's set this one up. Let's take a look at our function first. X squared plus y squared plus z squared is equal to rho squared. So rho squared raised to the 3/2 power would give us rho to the third. So we have 3e rho to the third. And then we have our extra factors of rho squared sine phi d rho, d phi, d theta. Now let's take a look at the limits of integration. First, for rho, the radius of this piece of the sphere in the first octant is going to be from 0 to 1. So rho is from 0 to 1. And then because we're in the first octant, the angle between the positive z-axis and the point on the surface will be from 0 to pi over 2. And then for theta, the angle between the points on the surface and the positive x-axis would also be from 0 to pi over 2. Now let's integrate this. We want to first integrate this with respect to rho. Notice we have an exponent of rho cubed, and then we have a factor of rho squared. This is going to require u substitution, where u is going to be equal to rho to the third. So differential u is equal to 3 rho squared d rho. And that's actually really good news, because if we look at our integrand, we do have a factor of 3 rho squared d rho. So if we write this in terms of u, we would just have e to the u sine phi du. This would give us e to the u sine phi. Well, e to the u is e to the rho to the third sine phi. And let's go ahead and do this on the next page. So we're replacing rho with 1 and then with 0. When rho is 1, we have e sine phi. And then when rho is 0, we'd have e to the 0, which is 1, so minus sine phi. Let's go ahead and factor out the sine phi. So we'd have e minus 1 times sine phi. And now when we integrate with respect to phi, that's going to give us a negative cosine phi. So when phi is pi over 2, cosine pi over 2 is going to be 0. So we'd have 0 minus, and then when phi is 0, this will be negative 1. So we'll have e minus 1 times negative 1. So this will just give us e minus 1. And now we'll integrate with respect to theta. That'll just give us e minus 1 times theta. So when theta is pi over 2, we'll have pi over 2. When theta was 0, we'd have 0. So it looks like we have pi over 2 times e minus 1 as the value of our triple integral. That'll have to do it for this video. We'll take a look at determining volume using spherical coordinates in the next video.